everyone. Today's lesson is going to be on substituted hydrocarbons, where we're going to build on our knowledge of hydrocarbons, which are molecules that contain only hydrogen and carbon, and there are a lot of different types. And we learned how to name a few of those in our last lesson. So today we'll build on that, and then we'll take a look at a couple of the reactions that can make some of these different types of substituted hydrocarbons. So we know hydrocarbons are just C's and H's. They can be very complex depending on the number of carbons that we have on them and the orientation of them. And we haven't gotten into chains yet, but there can be different chains just on hydrocarbons. But by substituting different components onto a hydrocarbon, we can create new types of organic molecules that would no longer be a hydrocarbon. For example, a halocarbon. If we remove an H from a hydrocarbon, we have an empty spot, an open spot on a carbon that carbon would like to satisfy and bond with something else. So if we put on a halogen or a group 17 element, we no longer have just hydrogens bonded to our carbons, so we no longer have a hydrocarbon. What we have now, since we put a halogen onto that chain, we have what we call a halocarbon, otherwise known as alkyl halides. And this is the way that you will hear me refer to them mostly, as alkyl halides. Now, IPOC is the organization that is responsible for the naming system, for naming these organic molecules, called the International Union of Pure and Applied Chemistry. We've heard of them earlier in the year as well. So the rules for naming these compounds, this is going to be probably one of the more important parts of what you're going to need to know with this, are the rules that you need to follow in order to name these molecules. So the first thing that we need to do is we need to find the number of carbons in the longest unbroken chain. And that'll help us determine the prefix of the parent name. And we'll do some practice with that in a second. Then next we want to look at the position of any functional group. This is what we're going to learn about today. This determines the direction of numbering because we always want to put that functional group on the lowest possible numbered carbon. And this functional group will determine the suffix of the parent name. Next, the position of any alkyl group will be considered. So if there's no other functional group, we'll look for alkyl groups, and that'll help us to name the molecule, as the alkyl group will then get the numbering priority. So first comes a functional group, second comes an alkyl group as far as naming priority. When we have two or more identical alkyl groups that are present on a hydrocarbon chain, we're going to specify, using Greek prefixes, how many of those alkyl groups we have on the chain, using prefixes like di, tri, tetra to indicate the number of those alkyl groups that we have. And we'll also specify the position as well. When we have different alkyl groups present on the chain, we're going to name them in alphabetical order. So if we have an ethyl group and a methyl group somewhere on our hydrocarbon chain, we're going to call it ethyl methyl. Ethyl first because it starts with an E compared to an M. So we'll consider alphabetical order. When a halide group is on a chain, each part of that name, the name, number, and position, are considered last. And those as well will be listed in alphabetical order. So an alkyl group, we've been talking about this, but an alkyl group is an alkane molecule fragment bonded to a hydrocarbon chain. For example, the methyl group is actually a methane molecule where we've removed one of these hydrogens. So if we get rid of that, we're left with what we call a methyl group. Since that carbon is missing a bond, has a lone electron to bond with, it can attach itself to a larger chain. An ethyl group, F meaning 2 carbons, is an ethane molecule that is still only going to have, one of its hydrogens removed, and therefore that carbon can then come on here and bond onto the hydrocarbon chain. And this can continue on infinitely. You can have methyl, propyl, butyl, pentyl, octyl, anything up to 10 carbons, which is really all that we cover that you're responsible for in this course. So those are our alkyl groups. A halide group is when we take a halogen atom, or group 17 atom, and bond it to a hydrocarbon chain. These ones are relatively easy to name. If we take a chlorine and bond it to a hydrocarbon chain, it's simply a chloro group. And this will be the same for any halogen, fluoro, iodo, bromo. Now to name these, they're relatively simple. We know that we have 1 carbon, so we know that we have methane, and we have a chloro group attached to it. So we're just going to add these 2 together, and we're going to get chloromethane. This one's a little bit different. Well, first we identify we have 1 carbon, so we know that this is a methane molecule, but we have 2 chloro groups attached to it. Those 2 chloro groups, since there's 2 of them, we have to call it di. So we know that it is 2 chlorine groups, dichloro. We'll simply add these 2 together, and we get dichloromethane. Now, similar idea here. First, identify how many carbons on our parent chain. We have 2. Our prefix for 2 would be eth, so this is an ethane molecule, and we have a fluorine attached to it, otherwise known as a fluoro group. There's only 1 of those fluoro groups. And with the halocarbons, we're simply combining these 2 together, so we get fluoroethane. Now, this part of the name can become rather large. And we'll see shortly that it can also get a lot more complicated. We can add a lot more different things to the chain as well. So again, with this example, we'll identify our longest unbroken chain. We have 2 carbons here, which is the prefix F. This is an ethane molecule. And we have 2 fluoro groups. So we're going to use the prefix di for difluoro. And both of these fluorines are on the N carbon. We don't have one of them that's over here. So they're both on the same carbon. And if you think about it, if one of them was on one and one on the other, we'd probably want to identify that. So we do that with numbers. Since both of these fluorines, we want to put these on the lowest numbered carbon possible, we're going to call this carbon 1 and this carbon 2. So this becomes 1,1-difluoroethane. So the numbers at the beginning are indicating where these 2 fluorines or fluoro groups are located. So we will indicate position with numbers directly in the name. Now this is a good example here. We have 2 carbons, so this is ethane. We have 2 fluorines, so it's difluoro, and we have 1 on the first and 1 on the second. And it doesn't matter how you number these, it's still going to be the same. We still have a fluoro on 2 different carbons. So this one becomes 1,2-difluoroethane. So you can see each part of this name indicates something. The carbons on which the fluoros are attached, there are 2 of those. F meaning 2 carbons, ane meaning this is an alkane and is all single bonded carbons. Not too bad. This example, we have 2 different fluoro groups. So first we identify our longest unbroken chain, 2 carbons. We have a bromo group, and a fluoro group. So 2 bromo or dibromo, and we have 1 fluorine. We generally don't call this monofluoro. Now the 1 bromine here is on 1 carbon, bromine on another, and the fluorine is on another as well. And we're going to want to try and put these on the lowest number possible. And we'll want to list these. I'm getting ahead of myself here. So we have our ethane chain. We went through that. 1,2-dibromo. So that's how we get the numbering priority for the bromine, 1,2-dibromo. And we have 1 fluoro group on the N carbon. And we'll want to put that on the lowest number possible. We would want to call this that. We don't want to call it 2-fluoro, 1,2-dibromo. We want to put each of our groups here on the lowest number possible. And we just add them together. 1-fluoro, 1,2-dibromo, ethane. A couple more examples. Feel free to pause the video and try these and check your answer. Our longest unbroken chain in the first one is 3 carbons. That is a prop prefix, and they're all single bonded, so that's propane. And we have 2 chlorines attached to this. One is going to be on the first. We'll number it in this direction as to put the 1 chlorine on the lowest number possible. So this becomes 1,2-dichloropropane. The next example, also a propane chain. But we have 2 chlorines, in this case on the first and the third, and it doesn't matter which direction you number that, it's going to be the same either way. Those 2 chloro groups we'll call dichloro, and it's on the first and third, so this would be 1,3-dichloropropane. Now in the next one here, this one looks a little bit different. We have 4 carbons, but we want to look for the longest unbroken chain. So we can either do that chain there, or we could do that chain there. Either way, this is a 3-carbon hydrocarbon. And if I'm going to take this, I guess it doesn't really matter, but this middle carbon here, central carbon, has an alkyl group off of it here. Or if we were to call the chain the L right here, this could be our alkyl group. Either way, they're both connected to this second carbon in the middle. So we could call this 1, 2, and 3. And we have this alkyl group off of the second carbon. So our longest chain is 3 carbons, and they're all single bonded, so it's a propane chain. And we have a 1-carbon alkyl group connected to the second, which we would call a methyl group. So we have a methyl group attached to a propane chain, and it's on the second carbon, so we call that 2-methylpropane. Another example, having a couple different chains on here. Again, we could look at this as 1, 2, 3, 4, or we could just go straight across 1, 2, 3, 4. Either way, on this third carbon, we're going to have 1, 2 single carbon alkyl groups or methyl groups. So this would be 2 methyls attached to a 4-carbon chain, which would be butane. And they're both bonded to the second carbon on the right side. Since they're both bonded to the second carbon, we want to number that as 1, 2, 3, 4, as opposed to the other way, which would put the methyl groups on the third carbon. This will become 2, 2 dimethyl, because we have two methyl groups, butane. So 2,2-dimethyl butane. Now the big question is, how do these different kinds of molecules get made? Well, hydrocarbons can undergo two simple types of reactions: addition and substitution reactions. And the products of these reactions are called hydrocarbon derivatives. They can also be called hydrocarbon substituted products or substituted hydrocarbons. This one is most common. So the first reaction we'll look at is substitution reactions, where we would take a saturated hydrocarbon, which is an alkane, so all single bonds between our carbons, and we're going to react that alkane with halogen. One of the halogens, remember that they're diatomic, so we'd have Cl2. It's not going to want to stay on there. We'd have Cl2. One of those halogens are going to replace a hydrogen on the chain. The hydrogen is also always the ones that are on the end of the alkane. That's one of the ways we can identify if the molecule that was made underwent a substitution reaction, because those halogens are going to be on the end of the molecule. And we have a one-for-one substitution, and that's how we get the name of a substitution reaction. So for example, if we start with an ethane molecule, single bonded, 2-carbon molecule, and we react fluorine gas with it, we can see that this hydrogen here gets kicked off and the fluorine substitutes on. And we're left with hydrogen fluoride gas with that remaining fluorine, which bonded with the hydrogen that came off. Now we can continue this process and add this fluorine even further onto the molecule, which would replace another hydrogen. And we would essentially end up with hydrogen gas. So taking a look at a example reaction, looking at the first reactant, we have C3H8 that fits the H2N plus 2 general form, which would be an alkane. In this case, it would be propane, since there's 3 carbons. And we see that we're reacting it with chlorine gas. Now we see that the number of hydrogens decreases here, and that hydrogen reforms with the remaining chlorine. So we can see that one chlorine replaces the hydrogen just by looking at the molecular formula. And that's relatively easy to see. Our number of hydrogens decreases, and we add a chlorine in place of that hydrogen. Now addition reactions are going to require an unsaturated hydrocarbon, which is a hydrocarbon that's going to have multiple bonds between carbons. In other words, we're going to have an alkene or an alkyne. Remember, an alkene is a double bond, and an alkyne is a triple bond. So if we take one of those unsaturated hydrocarbons and react it with a halogen, the multiple bond is broken, and now all of a sudden we have a bond that's been broken, and there's unpaired electrons which are looking to bond with something. So we can add halogens onto these newly open bonding sites. And if we compare the before and after, we started with this would be propene. It fits the H2N general formula. And we can still see that here. All we did was add the Cl2 onto the end. We simply just combined these two together. And this will look a little bit different once we look at how we can actually break that bond. Now in this case, this is also addition, because we're simply taking our one reactant here and adding both parts onto our 4-carbon butene molecule. So we see the hydrogens go up one because we added the one here, and the bromine got added on as well. So it doesn't necessarily have to be Br2. It doesn't necessarily have to be the same atom being added to the molecule. So this gives a little bit more of a visual on what's happening with these addition reactions. We have 4 electrons being shared here between these 2 carbons and ethene. And if we break one of those bonds, what we're left with is 2 unpaired electrons, which were just connected to each other, but we broke that bond, and it leaves 2 open sites to allow something to be added. Now, in order to add fluorine gas, remember we have to first break the bonds between those fluorines so we can end up with 2 unpaired electrons on fluorine. And this is not the easiest thing to do, but this will, since they're unpaired, it'll allow them to now react with the hydrocarbon and add onto that chain. And what we'd end up with here will be 1,2-difluoroethane. And that's how we get these halocarbons, either through addition or subtraction. And the key here is that addition is going to require an unsaturated hydrocarbon, and substitution will be a completely saturated hydrocarbon as far as starting material. The last thing we'll look at for today are aromatic hydrocarbons. These are relatively unique. They are cyclic, meaning that they are connected in a chain or a ring, and they have a property called resonance, where these double bonds look stationary, but they're actually oscillating or vibrating back and forth very rapidly. This is an example of benzene, C6H6, where the number of hydrogens equals the number of carbons. And this is generally the basis of most aromatic hydrocarbons, benzene, which is a nonpolar molecule. Looking at the structural representation of that molecule, the bonds look stationary, but they're actually oscillating or vibrating back and forth very rapidly. And we get this with these types of structures, like benzene. And it's similar, the resonance is similar to the vibration of a tuning fork when it is struck. And those bonds are actually going to oscillate or vibrate back and forth between their, go back to this here, between their other spots that I drew in here. And they're going to oscillate back and forth here very rapidly. If you guys have any questions, make sure you write them down and come see me for any answers.